have Geoff Penington. He's going to tell us about islands for outside the horizon.
Okay, so I thought it was important in the first talk of the year to set a good example that things don't have to be perfect. It's okay to talk about things when you haven't got all your ducks in a row necessarily, and so on. So that's why I started preparing this talk about half an hour ago. Also, I got bullied into doing this a lot because no one else wanted to, so I want to say that it's not my fault. Anyway, so yeah, this is some ongoing work with Raphael. I should say, so I think we completely agree on all the calculations involved. The interpretation of those calculations, in particular the question of whether firewalls exist or not, is we're maybe not so entirely on the same page on. So at some point we will establish an official party line of what the paper says that we can all agree on, but I don't think we've done that yet. So I'm just going to give my feelings on the matter, and Raphael can complain about anything he disagrees on. Firewalls don't exist. They're not a thing. Okay. So anyway, let's just sort of start. So let's start with the firewall problem. Because it's an interesting problem, even if the name is misleading. Okay, so we have a black hole, and it's spat out a load of radiation. We're going to be off the page time. All that radiation E. And we're also going to have some late radiation coming out here that we're going to call L. Okay, so L is some small system, and then finally we have the interior partners of L that's called A. I'm calling it A. I feel like people call it different things, but I can't remember what, so I'm calling it A. So, okay, the firewall paradox at its most basic is just a statement about monotony of entanglement. So the whole point is that semi-classical GR says that this L is highly entangled with A. Okay, that's because the state very near the horizon should just look like locally the vacuum state, and that's a property of the vacuum state. Meanwhile, unitarity, a unitary S matrix, the page curve going down, requires that L will be highly entangled with the radiation E. Monogamy and entanglement says that one system cannot simultaneously highly entangled with two different systems. I'm just saying this in some words, but if you want a sort of concrete one-step statement, then the natural one to use is just strong solid. We'll give you basically this with a quantitative meaning of highly entangled. But suffice it to say that these two things that satisfy that meaning, there's no way to have this be true with A and E being different systems as they would be in, say, GFT or anything like that, in a space-like system. So that gives you a few options for what you can do. Option one, which no one really seems to like these days except Bob Ward, but good for him for standing up for it, is give up unitarity. Just say, yeah, the whole problem here is that some classical GR says that this is not entangled with this, so it isn't, so everything's fine. Option two, give up classical. So this first one was giving up on L being entangled with E. Second option is giving up on L being entangled with A. That will also resolve the problem. So this is normally referred to as having a firewall, because if you just naively keep the same geometry but disentangle these two modes, then at least as you evolve backwards in time, you find that there's some very high energy stuff near this horizon. The third option, called complementarity, is A and E are not actually different. They're not independent quantum systems, and so they're not going to be entanglement. Can't be applied. So I don't think, well, other than Samir Mathur, I don't think that many people had actually thought about this specific normally entangled thing before 2012. But I think if they had, and at least in immediate response to firewall problem, a lot of people did just immediately say, well, it's obviously complementarity. Lenny explained to all of us, Lenny's system explained to all of us how this works in the early 90s, it's all fine. So it's just that A and E are actually secretly the same system. The trouble with this setup, which is different from previous setups where people would consider complementarity, like if something fell in here, you have this thing over here that's supposed to be the same as the information coming out here, is that these systems are sufficiently close together that one observer can go along the world line that sort of sees all three things. Okay? And in particular, that means you have a computationally unbounded observer. By which I mean an observer that has the magic power to, in a very short space of time, do some arbitrary complicated unitary. Obviously, all observers is unique, right? Okay. As I say, perfection is everywhere. You have a computationally unbounded observer that are allowed to magically do some decoding on this early radiation as they're jumping in, then they can distill the purification of L from E, carry it with them inside the black hole without it being bigger than the black hole, and then get three small systems, A, L, and E, all in their lab, in a pretty low curvature region of space, just inside the horizon of the black hole, and that lab would eventually have to contain an impossible quantum state. Low energy, low curvature lab. So we would like to say, even if globally the sort of structure of quantum mechanics, the space-like separated things commuting doesn't hold, at the very least, if you have some local lab in a region of space-time that's very low curvature, there's nothing locally weird going on, that your sort of 3 qubits or whatever they might be are really just described by ordinary quantum mechanics. I think if you're giving that up, you're giving up something really bad, and more than that, we don't even then know how to make predictions about the quantum mechanics of 3 random qubits if you happen to have just crossed inside a black hole or something. So that would be something really, really big to give up. So this was really the observation of amps in 2012. Namely, that once this distillation process has occurred, once the observer has done this complicated thing, which I want to emphasize is really, really, really unimaginably complicated. The complexity of extracting some nice small little purification of L out of E is exponential in the entropy of the black hole. Typical entropy of a black hole is like 10 to the 70, 10 to the 80, something like that. So we're talking E to the 10 to the 80. So it's not something you can do in practice. It's computationally unbounded. Observer is a sort of very, very idealized thing. But you basically can believe one of two things. he believes this distillation process works, and after they've done it, this is really entangled with their distilled qubit, then that observer could no longer see A entangled with L without breaking quantum mechanics in the lab. Okay, so if you wanted to believe in complementarity, you wanted to stick by option C, option 3, and not become a Star Wars believer or something, then you need to believe that a complicated operator on this distillation process, this extraction and purification of L, has changed A for integral or space-like separated. In other words, you've completely broken any notion of semi-classical causality in space-time. That's obviously bad. So we certainly won't want to say there's some preferred slicing into space-time. So the moment you start breaking semi-classical causality, then like, what actually happened, there's sort of no unique history to space-time at all. Just everything becomes ambiguous. Like when acting on E is changing something space-like separately over here, then when does it change it, right? There's no preferred time slicing that says it does it at the same time. It sort of could have done it up here, it could have done it down here, it could have always done it. It's just like it's all sort of hopelessly ambiguous.
Why is that? I mean, because the different operator in different space-time is a different operator in E. Of course, depending on what you do in E, that corresponds to
I'm talking about the same operator, like thinking about an operator happening on a Cauchy slice down here versus the time evolution of that operator happening up here. Right? Those are sort of the same operator acting on E, but where did it actually happen? Where did the change occur? Right? Just something acausal has happened and there's no consistent semi-classical history of what's going on if acting on E is changing something. I think that's reasonable to say. Do you agree with that?
But you can have any local operator here. And of course, when you can do it,
it's not. So if it's local on this slice, then it won't be local on this slice. But there will still be some operator on this slice, like say this mode, right? This outgoing mode, and there'll be some operator down here that does the same thing. So they're the same operator, so then at this time here, what's the answer? Is the operator being applied or is it not? I don't think there's a consistent thing you can say. This is to some degree summarizing a paper Raphael was writing, so this is my attempt to represent his point of view. I think it's completely accurate that there are a lot of problems that have to start happening once you start having these operators. I would say these operators are so incredibly complicated that it's sort of not surprising that you can make weird stuff go on by doing them, and there's plenty of other things even without gravity or anything like that, where if you allow complicated operators like reverse engineering someone's mind and erasing their memory and stuff like that, then things start getting pretty incoherent. Their experience gets pretty incoherent then too, so I don't really care, but it's totally reasonable.
You asked me to protest when we say something.
Yeah.
So I think that's a false equivalence, right? Because while I agree that we should not expect our everyday intuition to hold up to operators that, for example, turn you into a goat with memories of always having been a goat. But those operators act on degrees of freedom, where it is the case that if I act on the same degrees of freedom with a much more primitive operator, I will completely blow you up into a cloud of smoke. It's not something interesting like a goat. And here we don't want that to be the case, and that adds a huge layer of difficulty to making the whole thing work. Here we want it to be true that if I act on the whole radiation with a simple operator, like maybe I absorb it into a brick wall, then that will not do anything bad at the horizon. And it's only very special, certain very complicated things that have this magic ability to act non-locally.
Yeah, I think that is an important distinction.
I don't think so, but I thought this one, so I'm really wrong, but whether this applies before this or after this is, of course, then you can say it's an order of the local operator here, and after that, some local operator here. Whatever, however you just represent.
Yeah.
Or you're just going to do the opposite. And that's the same thing you can say in an E. So you just do some order,
So
and then
it-
something, and then the other order, and then the other way. But, okay,
But
that's what I thought.
I think if you have, if you want to try to actually interpret that in terms of an observer's experience, right? What do they actually experience?
Oh,
And you want that
yeah.
experience to be unique, then I think you're in trouble.
But yeah, but you complete the coordinator
Yeah.
and the EP formalism, and it's just simply the order operation. And you can do
Yeah,
the same.
yeah. Like as long as for there you're doing some in calculation or whatever it might be, then really what you're computing is observables in infinity. And as long as everything is really an observable in infinity, that maybe is saying something about what then happened inside, then things are unambiguous. But if you really want to talk about the experience of someone inside, then yeah.
Anything you can do for the EP formalism at the same level, then you don't see the problem. That's fine.
Yeah.
But anyway,
Right.
that's what I think.
Yeah. Okay. So, great. So I think.
Pull and push in the middle, or else bad things will happen.
Yes.
Great. So I think I've sort of summarized roughly the situation of the firewall problem pre-2019 or so. In 2019, we had islands, which certainly didn't resolve the problems I've just described, but I think they should be viewed now through a post-island viewpoint. So what does that say? Well, the most basic statement of islands is that using standard rules to compute entropys in quantum gravity, basically the replica trick, the natural way to compute entropys using the rules we know, you find that the actual entropy of this radiation E is given by a particular region, determined in terms of a particular region. So the island is like this, or I, where the actual entropy of this radiation is given by the so-called generalized entropy of union E island, which is equal to the area of the edge of the island. So the area of this surface here that's bounding the island, 4G, plus what I call S bulk of. So people sometimes get confused that you have an entropy of E sort of appearing on both the left and the right. This is a semi-classical, this entropy that you would have if everything was semi-classical GFT. This is the actual entropy in non-determinative. Okay? How is this region I determined? The answer is it's determined by what's called the QES prescription, which is that this quantity needs to be invariant under local changes in the ocean island. If you have more than one surface satisfying that condition, you take the one that has the smallest. Okay, so this follows basically from just applying the gravitational path integral. I'm not actually going to use these calculations at all, but I thought I'd at least say it since the first lecture of the year and it's a standard thing. At this point, the more interesting thing from our point of view is that the similar calculations using replica tricks tell you that given any semi-classical operator in the semi-classical state does something to the island, then there exists some operator. This is a non-determinative exponentially complex operator OE acting in the radiation such that OE acting on any state is the same as AI acting on that state. could put some V's in there, depending on the formulas we're using. But I'm just going to write this like this. So the effect of this operator acting on the early radiation is the same effect as on the semi-classical description, however we might interpret that, as an operator in the island. So for example, we want to measure something in the island, then there's an operator on E, albeit a very complicated one, that will do that measurement for us. Okay, so this obviously has implications for the firewall problem. In particular, you can just see that we evolve this A back in time, it ends up mostly inside the island. It's actually not entirely inside the island, and what we mean by A, but it's like, let's say 75% of the island, if we want to do a better estimate. So that means confined operators on the radiation that sort of do the same thing as operators on A. That tells you, that's semi-suggestive, at least naively, that this sort of complementarity point of view is right, and that A is not fundamentally a distinct degree of freedom from OE. It's actually just somehow the same degree of freedom. So, on the other hand, it's worth emphasizing here that this OI should really be thought of as just what that operator would be if everything is semi-classical. Right? The actual thing you're measuring here, the actual observable that you're computing in actual quantum gravity rather than QRT, is this operator OE, which is an operator on the radiation far from the black hole. So you're just seeing that indeed, this can be thought of as a test that indeed some operator on E is maximally entangled with L. There's some degrees of freedom in E that is maximally entangled with L. But someone who believes in firewalls, taking the option of keeping the unitarity, giving up on semi-classical GR, believes that anyway. So this is nice confirmation that they were indeed right to believe in unitarity, but it's no evidence that they were wrong to give up on semi-classical GR, because the only semi-classical stuff they've done here is just some mathematical steps in the calculation telling you that, say, something that fell into the black hole a long time ago is now encoded in the radiation. You're not actually saying anything direct about the experience you observe.
Yeah.
Yep.
Sorry, question. When you say that OE is the actual operator that you measure quantum gravity, so
Yeah.
is that OE supposed to be always some unitary operator independent?
It may be it could be a mission operator that describes a measurement. It could be some unitary operator. In both cases, like implementing it using a circuit or circuit and then doing a measurement will be exponentially complex. Yeah.
You can always perform some operation as an observer on E and measure the operator, or do you need to add some maybe a priori knowledge about the boundary map?
Yeah.
Something like that? Because
Okay.
for example,
There's a load of qualification I'd be missing here. You really need to assume you're in some relatively small code space. And again, yeah, because of the way, that's related to what I was saying, this is just, like, formally it's this semi-classical OI, right? Really, the way these operators work is that they're completely just sort of boundary conditions things. And, so like an operator acting in the island here is like, what it means is that if you started with a state formed by something falling in with a particle in state 1, and then you do a measurement, you'll learn it was in state 1, and you start with something falling in state 2. So it's really all determined by semi-classical GR laws applied to things outside the black hole. So you could imagine changing the dynamics inside the black hole by hand, and then it wouldn't actually change anything about how these operators behave. So that's the sense in which they're not truly necessarily telling you about what's going on in the interior, they're just telling you about what's encoded in the island. So at some level, I would say the firewall problem boils down to whether you believe that this island region is an actual physical object, and the people inside it, an observer inside the island really experiences stuff, an observer seeing the island, getting a signal up here, an observer up here getting a signal from the island, really that they experience that part of the space-time, or if it's all just some sort of mathematical fiction that is sort of a register that's keeping track of where certain information what information makes it out into the radiation, but it's not really actually a physical particle. Whether you believe that comes down to more to how unhappy you are giving up semi-classical GR, how unhappy you are that this semi-classical picture is so useful but isn't actually real, versus how unhappy you are with the fact that you can have these ambiguities if you do these experiments. Okay. So, as all physicists agree though, at the end of the day, the only real test of any question in physics, only something like this, is experiment. The only possible thing people might disagree is whether a thought experiment counts as an experiment or not. But regardless of whether we're considering thought experiments or real experiments, there's a big problem with doing an experiment and seeing what actually happens when you cross the horizon, which is you can't send a signal after infinity afterwards. You could wait until this person's in the island and then decode their experience, but again that's sort of circular. You're putting in by hand the semi-classical experience and then indeed determining their semi-classical experience with the semi-classical experience. So that's not definitive, and unless you can send a signal out to infinity, there's sort of no clean way of trying to answer this question. Okay. Possibly guessed from the title of this talk, the good news is that islands are not actually always inside the horizon. In fact, it's a very nice paper in 2019, not the M, the A from AEMM, but not the M or the M from AMM. So this paper, I feel like, there was a lot going on that year. This paper arguably got less attention than it deserved. Because it says something very radical. Okay, so what do they consider? They consider a black hole. And like many actual completely concrete calculations of the locations of islands, normally you want to make things as simple as possible, make the calculations clean. So you want the simplest theory of gravity you can find, and pretty much the simplest theory of the black hole you can get is Jason. It's a very popular thing to study these days. It describes two dimensions, one dimension space, one at time, in asymptotically anti-de Sitter space. So the infinity of this anti-de Sitter space is here, and then normally with islands, to make a black hole and anti-de Sitter space evaporate, you've got what's called transparent boundary conditions on. So the radiation coming out here just goes straight across this infinity of the anti-de Sitter space into this extra region. And this is literally just going to be quantum field theory of matter space. So these are glued together by boundary conditions. What AMM considered is a state where this flat space region is just in thermal equilibrium with the black hole. Okay, so not only do you have thermal radiation coming out of the black hole, you also have from the gravity region, the QFT region, you also have thermal radiation coming into the black hole from the flat space region. Okay, and then consider a radiation region R that consists of all these modes in the QFT region and the given time. So not just the outgoing modes, but also the incoming modes. Okay, so let's actually briefly just think about where the location of an island for this region could plausibly be. The first thing to note is that you have a time reflection symmetry here, which makes things easier. So that tells you that the island has to be sort of somewhere, could be a little outside the horizon, could be a little inside the horizon, but it has to be somewhere on this time reflection spectrum side. So it can't sort of be, the edge of it can't be in the interior, it can't be in the black hole, it can't be in the interior of the white hole, just because of symmetry. So Then you have the question whether it's outside or whether it's inside. One way to see it, so people often consider the actual setup they're considering here is really sort of a two-sided case where you have total symmetry. And you're actually not just considering this region R, but you also have this bar and the left boundary, or BL. So you're really considering the island of RL, BL, just R. One-sided cases end up being the same. But let's say we didn't have this R, we just looked at RL, BL, then by symmetry the edge of the island would be exactly the horizon. Right? But now when we add in R as well, that has to give you more information rather than less, so the island has to get bigger, so it has to go slightly outside the horizon. Indeed it does. What you find is that QES is order C bulk times G distance outside the horizon. Okay, so that sort of seems hopeful. If islands can be outside the horizon after all, then maybe you can just have some semi-classical experiment where someone jumps in and then goes back out and you can see all those sad things I said about never being able to tell about experiments and thought experiments about stuff real might be possible. There's a couple of problems. One, this is two-dimensional, so that's maybe not a problem, we're just doing toy calculation, but we'd certainly like to make it more realistic and confident. The other thing, the bigger problem, is that this is sort of an order Planck scale distance. It's an order G distance. In fact, in 4 dimensions, that's not just a Planck length distance, it's actually a Planck length squared distance. That's an incredibly, incredibly small distance outside the horizon. But there is another factor here, that's what I call C bulk. That's basically the number of fields you have, the number of two-dimensional fields you have in your theory. So if you make C bulk very big, then this can start getting bigger again. Okay. And now finally, double it.
That's coming in.
Sorry? Yeah, so, there's reasons to say that this is really the effective Planck scale. And so, it's still yeah, exactly. Yeah, so I think it's very reasonable to say that even if C bulk is big here, then you can't really send something in the same round. Yeah.
We thought that whether this is done in semi-classical regime, could come up with the very thing.
Yeah. Okay. So, finally ready to talk about actual new stuff. So, let's not consider any silly toy models. Consider a Schwarzschild black hole in 4D flat space. Or at least, modulus lambda much less than reference scales. I don't really care if it's actually secretly slightly anti-zeta or slightly zeta. So why would I care about this? Well,
What is it?
Sorry?
What is it?
Cosmological constant. When I say flat space, then you can put a tiny cosmological constant, but affects all flat space. So why 4D flat space? Why 4D flat space? Well, we live in 4 space-time dimensions and at relevant scales for black holes. Then the cosmological constant is effectively 0. Why Schwarzschild black holes? Well, all the black holes in our universe occur, and so we should really do that. But if any of you have ever tried to do a calculation with a curved black hole, you'll know why we didn't do it. So let's just think about Schwarzschild black holes. Much simpler. I think it would be exactly the same, but I'm not going to talk about it. Okay, so the great thing about a 4-dimensional black hole is you actually do have a large number of effective 2-dimensional fields there, right? Namely, if you expand the spherical symmetric space-time in spherical harmonics, then you have an infinite number of spherical harmonics, different angular momentum modes. Each of those describes an independent 2-dimensional field. So we might actually be able to get this large C bulk. The problem with all those fields, we have large number problem in normal, the reason you don't really have them in normal Hawking radiation is that almost all of them are just reflected back into the black hole. So the S-wave mode, for example, the zero angular momentum mode of a black hole can actually make it out. It has some probability of being reflected, but with order 1 probability it makes it out. But as you start upping the angular momentum, the probability of any of the radiation escaping in that mode becomes exponentially small. So what you basically have is erase this. This is now a 4D black hole in flat space. There's basically a wall, potential barrier that sits, maybe roughly twice the Schwarzschild radius of the black hole. And for high angular momentum modes, the really high potential barrier, you have zero possibility of becoming. So normally that makes all these modes irrelevant to black hole evaporation. But if you remember the setup in AMM, what you wanted to get the island outside the horizon was a load of ingoing modes and outgoing modes that are both in thermal equilibrium with the black hole. So actually having this black barrier is exactly what we want, because it's making all these modes be reflected, so they're actually in a thermal state in thermal equilibrium. So what we're going to do is we're going to consider island associated to radiation that includes all these high angular momentum modes. So this does mean that as a black hole is just evaporating normally, these modes are never out near infinity, they're coming out somewhere here and getting reflected back in. So we're going to have to consider radiation that is not way out here where gravity is basically switched off, which is the usual setting where you compute islands for, but instead we're going to define as a radiation region that includes all modes starting some more small radius, we'll call it R rad, just outside the horizon of the black hole. Okay? So there's a reasonable objection here. You might say it just doesn't make sense to compute an island of these modes at all. These things are inseparable from the black hole and making more sense, and so we just can't talk about them. I think that's wrong. I think it's wrong for a very simple reason. Namely, they only get reflected back in if you just let the black hole sit there. There are very standard methods for making it so that these modes actually all escape out to infinity. It's called black hole mining. The easiest way to do it, actually, is you take a load of strings that stretch from sort of here to here through this potential barrier, surrounding the black hole, lots and lots and lots of little strings. Radiation will just flow through it, will flow out to infinity. I mean, that's not a very high fidelity thing. That will only get you like most of the radiation, or like some of the radiation in that region, will get you a lot. And if you allow sort of put this thing in ADS-CFT, so to a tiny cosmological constant, then you can certainly do HDLL cell reconstruction. People are familiar with that, and just perfectly extract out all these modes. And you can do so, at least as long as this radius isn't too close to the horizon, without causing much back reaction and so on. Okay? So there will be a point where back reaction will come into play and so on, and this will start making no sense to talk about the island for these modes. But as long as this is sufficiently far outside the horizon, it should all be good, even if it's far inside this potential barrier. Okay. So, let's just compute where the island is for this situation. Okay? So, log into this formula, so I'm not calling it E anymore because it's not really early radiation. I'll just call it radiation. Okay, so the condition for the island, let me erase this. Right condition for the island is that delta Sgen of the radiation leaving the island is equal to 0, where this means the change in Sgen from a small perturbation at the edge of the line. Okay? In practice, we have a lot of symmetry in the problem here. So let's look at diagram. So if we look at this state, ignoring the order 1 angular momentum modes, which will give a negligible contribution to everything, the high angular momentum modes, the incoming modes, are in the same state as the outgoing modes. So you actually have an approximate time reflection symmetry here. You also have spherical symmetry. So if we have some spherical surface on a Schwarzschild slice, on the same Schwarzschild slice as the radiation region, then there's only one direction that we have to check externality. Everything else is fixed by symmetry. Anything that breaks the spherical symmetry has to preserve it by symmetry. Going forwards or backwards in time has to keep it constant by symmetry. The only thing we have to check is what happens when, so this is our radiation, so our QES, the island is somewhere further in here. So that's our QES, our radiation. The only thing we have to check is what happens if we move our QES a bit outwards. Okay? So we need to have a condition for the island is that the Sgen radiation in the island by the RQES has to be equal to 0. Okay? Phil, did you have a question?
No.
I thought you were pretty good. Okay. Great. So all we need to do is compute this Sgen radiation in the island is equal to the area, the edge of the island, 4G, plus bulk of radiation. Okay, so let's start with this area here. Okay, I'm going to switch from R is a not very good coordinate in the horizon, so I'm going to switch to a coordinate rho. It tells us the proper distance outside the horizon. Okay, so what is the area of a spherical surface as a function of rho? Well, area function of rho is going to be equal to area of the horizon plus something. It gets bigger as you perturb away from the horizon, right? This is a minimum here. If you go this direction, it gets bigger. If you go this direction, it gets bigger. So the linear term vanishes. So I'm just going to Taylor expanding rho because rho is going to be very small. Everything's going to be very close to the horizon here. So the radiation will be very close to the horizon. So we're going to get something that's order rho squared. Right. And what is the, to make the units work, in general d dimensions, we'd need, this would have dimension d minus 2. This would have dimension 2. So we need an extra factor, dimensional analysis. The only one relevant scale is the radius of the black hole to d minus 2. 40 centimeters. And then there's
I can't read any of it.
put it over here so it's closer to you, right? Okay. So, this is the area, very large letters, for those whose eyesight is getting weak with old age. As a function of the proper distance outside the horizon, zeroth order is just the area of the horizon. First order, it vanishes by symmetry. Second order, we have something proportional to rho squared. Dimensional analysis, we need to match the dimensions of here and here. So we have the radius of the black hole to d minus 4. make the dimensions right, and then there's some free factor that I'm not going to care about that has to do with spheres and d dimensions. Probably involves something stupid involving pi. So let's not worry about that. That's what that looks like. Okay, the second thing is how this thing depends on this RQES or rho QES. So this is rho QES, it's the edge of the island. So we're considering the semi-classical entropy of all this stuff in the island, which is all the rest of space-time. Maybe this black hole's formed from collapse, whatever. Doesn't really matter. All the stuff there, union, all this stuff outside here. Okay, the global state of space-time is pure, so that is actually equal to the entropy of just this little bit between the edge of the island and the start of the radiation region. Okay? The end of the radiation region is already very close to the black hole horizon, so this is some very thin little slab. Roughly looks like it's like a sphere. Okay. Looks like some thin, narrow thing, where this is at our radiation, this is at RQES, and then this is all glued together so it's a sphere. I just showed a chunk of it. Okay? So what we really want to be doing is bulk equals the entropy of the slab with cross-sectional area, the area of the horizon, and width of the slab is rho radiation minus rho QES. Okay? This thing has a standard formula. It's two leading pieces. The first is just a divergent piece that's proportional to the area, the cross-sectional area, over some cutoff, it's the d minus 2. Okay? This is the standard area law of entanglement entropy. Importantly, this thing doesn't depend on this at all. So from our point of view, it's just some constant that would eventually get renormalized into the area to get some finite. We don't care about that. The interesting term is you go minus the cross-sectional area divided by the width of the slab, d minus 2. Okay, so roughly, this is just as the slab gets narrower, the entropy gets smaller, there's fewer modes in it, and yeah, the derivative with respect to width of the slab is some finite thing, dimensional analysis is a sort of obvious thing. If you want to actually compute this thing, there's a couple of good ways to do it. If you make your bulk Q of t be holographic, you can just use RT. If you want to do it for like free fields, you can just expand in terms of spherical harmonics, 2D spherical harmonics. Those each will become like a massive two-dimensional field, and then you can just add up the entanglements with all the massive 2D fields using the standard 2D QFT formulas, and you'll get exactly this is being done. Okay, so yeah, sorry, there's a prefactor at the front here. There's some universal prefactor that can be computed, but it's not anything terribly nice, so I'm not going to bother writing it. But this is the scaling. Okay, so now we're going to solve this equation. So we want to set the terms that matter, the terms that depend on rho QES, for this one and this one. So we have the derivative of this thing gives us RBH to the d minus 4 rho QES. This one this has a minus sign, and it's order A horizon over rho radiation minus rho QES to the d minus 1. And this is supposed to be equal to 0 at the island.
You said zero.
Yeah, this was the area term. I computed just for the the area here, but then we actually wanted area before. Okay, so the 1 over d. Good. Okay, so for simplicity, we definitely want rho radiation to be bigger than rho QES. Let's assume it's like much bigger. Let's solve this thing very, very schematically. So we have R, VH, 4, rho QES, over G goes as R black hole to D minus 2 over, so rho radiation is much larger than rho QES. We can just treat this as roughly rho radiation. Rho radiation to D minus 1. So this gives us rho QES scales as G R black hole to 2 over rho radiation. If I've done stuff correctly, this G scales like area, so we get an area d minus 2 plus 2 is d divided by d minus 1, which is the distance. Great. I'll call that a victory. Okay, so this tells us the distance of the island. We find indeed that it's sort of Planck naively in order g, so in order O Planck squared distance outside the horizon, very, very tiny. But if we make this thing small, then it can get bigger quite fast. Okay? So the question is, how big can we make it? Well, obviously, we need to have rho radiation much bigger than rho QES, but let's set that to be big, but like order. Okay, that's, we're talking a bit about whether we can even get this close, or whether something dodgy is going on before that, but we can't get any closer than this. Okay? So in that case, parametrically, we just have rho QES d, so these are parametrically the same. Scales as g R black hole squared, rho QES scales as g, so 1 over d R black hole, 2 over d. Finally, just go to 4 dimensions. This is the square root of O Planck. So this is, I think, really surprising. I think we were certainly very surprised when Raphael first computed it. I thought it would go from like O Planck squared to like O Planck or something, and it's like still not interesting. But this thing, if O black hole is like sufficiently big, if you were like actually in asymptotically flat space and you just had an insanely giant black hole, this could be light years, it could be billions of light years, it could be arbitrarily big, arbitrarily far outside the black hole. The acceleration required to sort of fly in there in your rocket and then fly back out is negligible. You'd have to keep going for a very long time, so you'd have to really make it in and then out. So you'd probably need refueling and stuff lots of times, but you can do that. Totally practical to just go in and go back out with a macroscopic observer. And yet this is apparently going in the island region of the black hole. In our universe, of course, black holes don't get arbitrarily big, but if you plug in the radius of the largest known supermassive black hole, then this thing ends up being something like 10 to the minus 11 meters. So we're talking atomic scales here. So you couldn't actually jump in even if you could get to a supermassive black hole, and that's not even the Milky Way galaxy one, it's like some even bigger one, but Milky Way galaxy is close enough. So you couldn't actually fly into that region and fly back out. But you could certainly, at least theoretically, in a thought experiment, imagine doing some scattering experiment that's going to probe that region and not have it involve anything comparable to quantum physics. It still involve like electrobeats physics, something like that, and nuclear physics. Really quite low energy scale. Okay, that is the punchline of the talk. I think that's pretty exciting because I hopefully set up to you guys that the big reason you could say who even knows if there's a well-defined answer to whether a firewall or does it even matter is because the external universe can never know about the answer to the thought experiment in the first place. I think when you have an island, yeah, so let me just make a few comments about what this means, doesn't mean. You have an island out here, something in here, okay, and you have radiation here. Naively, it just seems totally paradoxical that a signal from here, some macroscopic signal, can go out to infinity if it's secretly not independent degrees of freedom from no radiation. Right? Because signally you can get everything out to infinity, and then you just have a cloning paradox, because the information should be in here, should also be in here. The reason that doesn't happen was already explained by AMM very nicely. The answer is that, remember, this radiation that we're talking about includes stuff that is falling into the black hole, right? So I said, okay, you can mine it and then it won't fall in. And the mining will not create much back reaction, but it does create some back reaction. It has some back reaction on the horizon. If I insert my threads, I mine here, just imagine, nothing crosses this wall anymore. That creates a back reaction on the horizon here, and what you'll find is the horizon comes out to at least here, and so this signal, because I've decided to keep this radiation outside the black hole, get it off to infinity, then I can no longer get the extra copy of the radiation that was in the island. Okay? So, one response you could make to this, is actually Domorov's response to me, though I'm pretty sure he won't stand by it if I have time to argue with him enough, is that maybe it's actually this extracting the radiation that is creating a firewall, and so a firewall only forms with it inside the horizon. It wasn't there when it was outside, but then it is once you do this. This whole extraction process can be done space-like to the island, and space-like to the back reaction of the horizon. So if it was going to create suddenly a firewall at the horizon, it would be doing so in an acausal non-local way. And so that would be not only as bad as complementarity, but much, much worse. Because, I mean, mining a black hole is not very easy, but it's fundamentally a semi-classical process that does not involve any exponential complexity or anything like that. It's independent of G. You can take G strictly to 0 and it will stay in order 1 complexity. So that would be the vastly simpler thing causing exactly the same sort of non-local physics. So that's not a not going to happen. But yeah, so that's one thing you could ask about, is just extracting all this radiation and then sometime up here you do something to it. If you do that, then the information will be there, but the back reaction is in the same copy. But you could also ask, what about if, as in the AMS experiment, I just imagine that I have infinite computational power, I can do any unitary I want to the radiation just at this time here, and I do let it fall in, I just do something very complicated first. In particular, can I do something very complicated that changes the state of this thing flying out? For example, someone flies in with a qubit in the +1 state with their rocket, and then they fly out. Can I change it so that the qubit has changed from 1 state to the 0 state? And the answer is that yes, if you believe in island calculations, and then control calculations that involve, they involve sort of formally extracting this radiation to infinity, doing something to it, and then putting it back in, all interpreted as just a unitary acting on this, and doing this replicator scale thing. But yes, you can just change what happens here. So doing this very complicated thing means that the person flies out. So yeah, what are your options then? One of them is to just learn to love complementarity and exponentially complex things causing all sorts of weird stuff in black holes. The other one, I think, is to believe that there is just always already a firewall, or at least this far outside the black hole, and so this whole region is vacant. So then there's sort of two options. Depends on the... If you really still want to say that semi-classical physics is great for giving calculations, even if it's not like physically real beyond this region, then probably what you would want to say is that space-time ends here, there's a firewall here, but if someone jumps in on a rocket with the intent to fire their rocket and go back out again, then even though they hit the firewall and die, then a new version of them on their rocket will jump out here and appear zooming out, and hence semi-classical physics will give the right answer to infinity. If you want to, like, yeah. So I think most people would agree that's totally perverse, and if the firewall has weird enough dynamics that it knows to do that, then you should just say that the semi-classical region behind it is real, right? The other option is that even if the person, you do a scattering experiment and shoot something back out, or in a physical situation where you have large enough black holes, so it jumps in and then plans to come back out, they just die at this firewall, they never come back out, and everything's stabilized. In that case, you have a semi-classical calculation, what should be happening as they jump in and then zoom back out, but it's just being wrong, that it's not even involving things blanking close to the horizon, it's parametrically far outside the horizon, albeit small compared to the horizon radius. Yeah, so that's a pretty radical giving up of semi-classical GR. You then have the question of why the island calculations work at all if semi-classical GR can't even get that right, which doesn't involve any complexity, it's just completely Lorentzian classical dynamics of someone shooting a rocket. Why on earth does it get things like HEP right? I don't want to. I'll defer to Raphael on what the firewall answer to how that's satisfying is, because I'm not going to try to paint that point of view. I think it's wrong. But I think that's the situation. So I find this really exciting because you really can. With the semi-classical thought experiments that fundamentally involve things beginning and ending in infinity, and so actually don't involve like circular reasoning or making up a dictionary for what happens inside, then you can really determine whether there's a problem, at least whether there's a meaning. So yeah, thanks guys.